Any questions? Oh, okay, let's talk about how our end game is going to be. Okay? First, let me repeat this because I didn't have Screencast-O-Matic on. Please, everyone, do your student course evaluation. Please, okay? You can wait till after you see the final grade if you want to. However, I know when I was a student, once that last final was done, I turned the brain off and I was heading home, and I wasn't thinking about anything else. So don't get in that mode. Be sure you do the student. Oh, man. Okay, I found out that worked in the last class. I couldn't get anything else to work, but what I did was that. Okay, when electronics don't work, bang on. Okay, that's the cardinal rule. Okay, so let's go to the current slide. We are recording, so that's good. All right. Now, let's talk about our end game here. We're going to get as far as we can in Chapter 6. We're already in 6.4. Hopefully, we'll finish that today, and then may even get into 6.5. And if we do, great. If we don't, it's okay. I've already made out the test, so I may not have put enough questions on it, covering enough material, because I wasn't sure how far we were going to get today. But if we do more than what's on the test, that's okay too. So, at the end of the class today, I will give you 2 tests. One will be the Chapter 6 test, Test 4. The other will be your comprehensive final exam. And they each have 10 questions, I think, if my memory's right. And they're pretty straightforward, I think, for Chapter 6. Shouldn't take you too long to do that. And then the final exam, if my memory's right, I did 3 questions from Chapter. Let's see, how did I do it? Probably 4 questions from Chapter 1. I don't remember. Chapter 4, 3 from the next 2, or something like that. So I broke it down somehow, but it's the first bunches of questions are questions like what you've already had before, not the same questions, covering the same material, and then just a few questions on Chapter 6. Okay, maybe 2 or 3, I don't remember now. All right, so any questions? Those are due. Oh, let's hit this. Are any of you graduating this term? You are. Okay, any of the others? Now, the bad news for you, it may not be bad news, I have to have your both tests in by the first thing Tuesday morning. So, preferably sometime Monday. I'll be here on this campus Monday from, okay, let me give you the rest of our schedule. Okay, my office hours today, I have this class. As soon as this class is over with at 11:15, I'm free until 3:15. At 3:15, I have another class that goes until 7:45 in the evening, so I'm not free after that. Okay. Tomorrow, Friday, I'm not going to be on the Birmingham campus. And don't think I'll be on Birmingham campus anymore this term, because the building where my office is still been closed, as far as I know. Have any of you been to the Birmingham campus recently?
Yeah, you and B building?
B building? Yeah. I don't have an office. I have an office there, but I can't get to it. Okay, so I'm going to be here on Bessemer for the rest of the term. Okay, so I'll be here tomorrow from 8 o'clock until 12 o'clock. I'll probably be here before 8. I'll probably be here after 8, but officially I'm here 8 to 12. I'll probably be here after 12. But officially, I'm here 8 to 12. So you can turn in things in if you want to. Monday, I have a review session with one of my classes in this room from 8:30 until 10:20. Okay? So I'm out of the pocket then. I'm on campus, usually by 8, before 8. But I'll be up here from 8:30 until 10:20. Other than that, I'll be in my office. Okay, 265. Now, if students come in to do makeup work, then I'll probably go to a classroom, maybe this classroom, or possibly a classroom somewhere between 265 and here. whatever is most convenient for the student and for me, closer to my office, I'll take the classroom down there. Okay, so if you don't find me in 265, look in all the classrooms between 255 and here. Okay, 265 and here. Now, on Tuesday morning, I really need, Walter, need it before 8:30 because I'm giving an exam at 8:30. That's going to be down in 255. I mean 205. So if you haven't gotten here before 8:30 on Tuesday morning, bring it straight to the thing. Don't wait for me to get there because I've got to get yours graded so I can turn in your grade by noon. So your grades have to be in by noon on Tuesday. The rest of you, you have until Thursday. Okay, let me give you the rest of my hours then. On Tuesday, I'm giving an exam from 8:30 until 10:20. May go a little later than that, but I don't think so. And then I do have a class at 3:15 again. So, and I'll be giving a test. Now that's a mini-term class. So we're doing a lab first and then possibly a test. Okay. So I won't be here, I don't think, in this room until 7:45 at night. But I will be. The class officially runs in. But since we only got to do one lab and one test, I imagine we'll be through well before 7:45. So if I'm not in the room here after 3:15, I should be in my office. I'll be here until 8 o'clock at night. Okay? So on Tuesday, you have until 8 o'clock to get it to me. Wednesday, I do have a test. I'll be administering a test up here from 8:30. Well, okay, I'm not going to say that. I easily could be administering a test here from 8:30 until 10:20. I may not be. If all the students come in earlier, then they'll already be taken care of. Or if they don't show up, I may be in a different room. But Wednesday, basically from 8 o'clock in the morning until 4 o'clock in the afternoon, I will be somewhere between 265 and 255, somewhere between the giving tests or in my office. At 4 o'clock on Wednesday of next week, I head over to the Birmingham East Campus because I'm collecting tests over there from my physics class. So I'll be there from 4 to 6. So if that's more convenient for you, Birmingham campus 4 to 6, well, actually, I'm driving from here to there from 4 to 4:30. So I'll be there from 4:30 until 6:30. Usually a little after 6:30, but at least from 4:30 to 6:30. So if that's more convenient for you to bring the test over there, I'll be on Birmingham East Campus, the Ethel Hall building, that's the nursing or health professions building, in room 103, right next to the restrooms down on the ground floor. Okay, if that's more convenient for you. Then on Thursday, I have no exam scheduled. There could be students coming in doing makeup work. If they are, I'll be either in my office or somewhere between 255 and 265 from 8 o'clock in the morning until probably pretty close to 8 o'clock in the evening. Please get me your work sometime before 8 o'clock Thursday evening. Now, I will be on this campus Friday morning. I thought the graduation was going to be Friday morning, so I thought it was going to be on Birmingham campus all day. But I think the graduation is at 1 o'clock. Is that right, Walter? Yeah. Okay. Well, what time do y'all have to be there?
They ain't told us yet, but they told us we have rehearsal at 12, so I guess we forgot that day.
Okay, you still don't know. Another student told me she heard they had to be there at 10 o'clock. I'm not planning to be there at 10 o'clock unless they tell me I have to be there at 10 o'clock. Okay, so I'm planning to leave here by 11:30 to be over there by 12 o'clock. That way, if there are any instructions, I can figure I can get it done in an hour. Okay, and graduation from 1 till probably 2 or 2:30. I don't know, something like that. After that's over, I'm going home. Okay, so I won't be coming back to Bessemer. So if you can't get me the stuff by 8 o'clock Thursday night, get it to me by 10:30 Friday morning. I'll be here on this campus from 8 till 10:30 approximately. If I hear I have to be there sooner, I'll go sooner. But please get it to me. If I happen not to be in the office and you can't find me, you can always slide your work under the door. Okay? of my office. And that way when I come in the next morning, whenever that is, even Monday morning, I have until noon to get your stuff done. I cannot accept it any later than Monday morning. I mean, when I come in, if something is slid under my door on Friday, I'll grade it then. But then I'm going to be crunching numbers for the rest of the morning, trying to get the grades in. Okay? And Walter, I've got to have yours in by first thing Tuesday morning. You know, not that Tuesday, this coming Tuesday. All right. Any questions? All right. Any questions on trig, by the way? All right. Now, I have that we hadn't done example 2. Did y'all have that in your memory bank as well? Okay, good. Okay, you sound so excited about it too. Okay. So, let's do example 2. It's not on the slide set, so let me get set up for this. All right. Here we have vector u, not necessarily a unit vector. In fact, definitely not a unit vector. It has, in component notation, -1, 3. You see why I say it's not a unit vector? The magnitude is way greater than 1. It's 10, or square root of 10. Okay? Vector v is 2, -4. And you wouldn't even guess that would be a unit vector. And vector w is 1, -2. All right. Okay, good deal. Now, it said find each of the following quantities. Okay? The first of these, the A one here, is what is u, vector u, dotted with vector v times vector w. Okay? Now, you tell me right off the top, do you expect this answer to be a scalar number, a vector, or what? You don't have to know the answer. I just wondered if you had a guess. It will be a vector. Your final answer will be a vector. Okay? What do you think you should do first? Okay, plug in the vectors. That sound okay? So we'll do vector -1, 3 dotted with vector 2, -4. Whoops. I'm getting my symbology crossed up here. Okay. Close bracket, parentheses, and then vector 1, -2. Now, what do you think you should do first here? Do the dot product first, because that's in parentheses. You still use that same typical thing. Please excuse my dear Aunt Sally. Let's do parentheses first. What do you get when you dot two vectors? Okay, but what is going to be your answer? A vector or a scalar? A scalar, okay? So tell me what you mean by adding them together. What do you add together?
The product of multiplying.
Yes. -1 times 2 what next? Plus 3 times -4. Okay? Now I'm putting the dot in there. That's not a dot product because these are just numbers, but I'm just putting it there so you can see what's going on here. So the first, and then this thing will multiply by 1, -2 at the end. But let's first do the dot product. What does that give you? -2 minus 12 times 1, -2, component-wise, and this will be -14 times 1, -2. Now that's sort of an all right way to write your answer. I would accept that. But if you were doing it on WebAssign, they may not, and you wouldn't know why. They would just tell you it was wrong if they didn't. What would that be if you took it one more step? 28, perfect. Okay, let's see how the book left it. They left it negative 1428. Do you see how to do that? Any questions on that? Okay, got it, everybody? Pretty exciting stuff, isn't it? Okay, so I'm going to erase parts of this. Big parts of this, in fact, almost all of that. Okay, so that was the A part. Let's move to the B part. The B part says, start with vector U and dot that with 2V, or not 2V, okay. And how do you do that? What would be your procedure? Vectors, so that would be negative 1, 3, there's your U, dot that with 2 times vector V, which is 2, negative 4, okay? Now really at this point, it doesn't matter the order. I'm tending to do it the way it's described here, but if you go back to your rules that we just did on the previous page, on page 429, you see if you have a scalar multiplied by that number 5 on that previous page, right at the middle of the page, what we have is u dot CV. You could write it in any one of those 3 forms. I'll write it just like we did it. What would that be? Negative 1, 3, dotted with what? Now that is a dot product now. What would be 2 times 2, negative 4? 4, negative 8. You just scalar multiplication, and then your dot product would produce negative 4 minus 24. Perfect. And that produces what? Negative 28. You do get a scalar answer there, and that's what it is, negative 28. Good for them, they got it as well. All right. There is a C part. Any questions on this before I erase it? Anybody? Okay, let's erase this and do the C part. Now, this looks like it's we're going backwards here. It says the magnitude of vector U, because we've been doing that since the beginning of the vector, the last section. But there is a new way to do a magnitude. Let's do it that way now. Does anyone remember what the new way to do a magnitude? Okay, magnitude squared is what? U dot U. You're absolutely right. Okay, so let's do U dot U, and what does that become? U dot U. U is, or U are, negative 1, 3. Oops, I did it again. Dotted with negative 1, 3. Dotted with itself. And what does that give you? Negative 1 plus 9. 1 plus 9 is 10. That gives you magnitude of u squared. So what is magnitude of u? Equal to the square root of 10. I think we must have done that sometime in the past. It seems like we have. And sure enough, that is what you got. All right. Good deal. There is a checkpoint following, and that has 3 additional problems. I highly recommend you do those as soon as you can after class, just to get it nailed in your head. Oh, that doesn't sound good, does it? Okay. So now we're ready for, if there are no questions on that, the angle between 2 vectors. Okay. Now, what we're going to do at this point is give you another definition for a dot product. The definition we gave before is perfectly good, legitimate, and everything else, but it doesn't tell you beans about the relative positioning of those vectors. It just gives you a number. Well, there's another definition that does give you different information. Okay? And leading up to it, let's think about 2 vectors here. Here's a vector v off in this direction. Here's a vector u off in that direction. Now they wrote these as in standard form with the initial point of each of these at the origin. And when you do that, the angle between 2 non-zero vectors, remember a zero vector has no magnitude and no direction, so you can't really talk about an angle between it and anything, because which way is it pointing anyway? We don't know. Okay? But the angle between 2 non-zero vectors is the angle theta, and it's always going to be between 0 and pi. So even if you had drawn vector u down here, you don't carry it all the way here, you make your angle the smaller of the 2 angles that you can draw between these. So in other words, this is not your theta, that's your theta. And if it was down here, that would be your theta, not that. So you always stay between 0 and pi. Okay? Now, it can be equal to pi or equal to 0, either one. Equal to 0 means it's on top of v, and equal to pi, that would mean it's exactly collinear with v, but pointed in the opposite direction. So those would be the extreme cases of theta. Okay. So the angle between 2 non-zero vectors is the angle theta between 0 and pi. And frankly, this looks wrong. It looks like they put the 0 vector, because that looks like it's bold, but maybe it's not. I don't know. No, I guess it's the same as these numbers. So yeah. Okay. Between their respective standard positions, in other words, you put them both as with common initial point of the origin. Okay? And you can find that angle through a different definition of the dot product. And here's, well, they don't show it this way, but this is actually, if my memory's right, and it's been a long time, I think this is the first definition I knew of a dot product. That u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle in between them. Okay? That is another definition of a dot product. Okay? Notice this is a magnitude, scalar, that's a scalar, and that's a scalar. So your dot product comes up being a scalar. Well, rearranging that, you have the cosine of the angle in between is the quotient of the dot product divided by the magnitudes of the 2 vectors. Okay? So that's how you get the angle in between. Cosine of that angle is this, so the inverse cosine of this is that angle. Make sense? Using your inverse cosine. For a proof of the angle between 2 vectors, you can see proofs of mathematics way back on page, well, it's the end of this chapter, page 464. Okay, so let's move to example 3. And this example is also found at larsonprecalculus.com, there's an interactive version for this type of an example. It may not be exactly the same, but pretty close. So U is the vector 4, 3, and V is the vector 3, 5. Shown here on the, both being in the first quadrant, okay? Because all your components are positive. So you're in the first quadrant. The angle theta is a pretty small angle here, apparently anyway. So let's see what that angle is. According to the last definition, how do we begin? Cosine of that angle theta is what? Dot product of U and V divided by the magnitude of U times the magnitude of V. Okay? Now, do you need to write it out, or do you think you can just do these that dot product just like we have? Fine to write it out if you need to. What do you think? Okay. And what would you write out?
4, 3.
Second? Okay. Oh, you mean right up? Okay. 4 comma 3. 3 comma 5 over what? Okay. In other words, U dot U. Can you do that in your head right now, or do you need to write it out? Okay. 4 squared is? Plus 3 squared is? 15 plus 16 plus 9 is? Second? Not 23. 25. Now what's square root of 25? 5. So that would be 5. So you already did the square root, okay? And in the next one? 34. Okay, there's your denominator done. Let's do the numerator now. What would that be? Okay, 12 plus 15 is 27 divided by 5 root 34. Okay? Punch that into your calculator. 27 divided by 5 divided by root 34. Just as a general looking at it, that's 27 divided by something just a little bit less than 30. Okay? And then do an arc cosine for it. All right. Here's Josh. Okay. I gave out tests that have been turned in already. And you had done test 1. Not test 2, so at the end of the class, come get test 1. I'll need your other tests Okay, today. Okay. All right, we're finding the angle between two vectors using the dot product and the magnitudes. What do you get?
The angle is 42.17.
It's what?
42.17.
Okay, so that gave us a number, and then when you took the inverse cosine of that number, you got 22.17 degrees. Now, I kind of disagree with that many digits. I think I would have said about 22 degrees. Okay, I don't think you can get 4 significant digits out of nothing more than 1 significant digit, but it's okay. The book probably did at least that many. Yeah, they did 22.17. Oh, I see. Okay. Degrees, which is also, if you had done it in radian mode, about 0.3869 radians, which again is more digits than you can justify. All right. Any questions on that? All right. Again, there's a checkpoint. I would certainly do that shortly after class is over, as soon as you can, while it's fresh in your mind. Okay. Now, let's see how they did it, because the problem is here. Cosine theta is the dot product divided by the product of their magnitudes, which is 4, 3 dotted with 3, 5, just like we did, divided by the magnitude of 4, 3 times the magnitude of 3, 5. And that would be 4 times 3. Now, don't get them crossed up. If you looked at this to define what your dot product was, you're probably going to get a very bad idea. And that's for this reason. This 4 here is being multiplied by that 3, not this 3. Okay? So don't look at this and say, oh, that's how you do a dot product. It looks like you multiply these 2 and those 2. You do not. Okay? It just happens to be they have a 3 in each place. It's this 4 times that 3 plus this 3 times that 5. Okay? And then the magnitudes, of course, use those same ones. 4 squared plus 3 squared, 3 squared plus 5 squared. And that would give us 27 over 5 root 34. Okay? Now, that implies that the angle between those two vectors is the inverse cosine of that number, whatever that turns out to be. If you're in radian modes, that would come up 0.3869 radians. Again, more digits than you probably are justified in. And, whoa, they didn't even do the degree, did they? We did, the book did, what that would be in degrees, 22.17. Or I would say about 22 degrees. Okay. Now this is what I just told you earlier. They're doing it now, which is fine. It leads to another definition of a dot product. It's the magnitude. They call it alternative form for the dot product. I call it another definition. It's the magnitude of u times the magnitude of v times the cosine of the angle in between. Produce an alternative way to calculate the dot product if you happen to know one or more of those things, then that would be the easier way to go. From this form, you can see that because the magnitude of u and magnitude of v are always positive, u dot v and cosine v will always have the same sign. So, because these two are always positive, whatever your sign of this is, that's got to be the sign of cosine theta, or whatever the sign of cosine theta is, that's got to be the sign of your dot product. Okay. So here are 5 possible orientations of 2 vectors shown here. And again, I mentioned this before. If v and u have this initial points, and one's going exactly the opposite direction of the other, there your theta is pi, and the cosine of theta is -1. Okay, so that means these 2 vectors are going in exactly the opposite direction. The dot product is going going at an obtuse angle from each other. Not opposite directions, but an obtuse angle between the angles between pi halves and pi. And so therefore your cosine is always going to be negative if that's the case. And if it is, then you have an obtuse angle, because that's the only way you get an obtuse angle between 0 and pi if the degree is between pi halves and pi. Okay? That will give you a negative value. So if your dot product is negative, you know you have either an obtuse angle or exactly opposite direction, which is also obtuse, by the way. Now, if your theta was exactly pi halves, what is the cosine of pi halves? 0. And if that is the angles of pi halves are 90 degrees, you have a right angle. The dot product is always, this is important, always 0 for right angles. Or the other way to express it, two vectors are orthogonal to each other, meaning perpendicular to each other, at right angles to each other, any way you want to say it, then the dot product is 0, because the cosine of 90 is 0. And Jalen's here. Okay. Perfect attendance today. Had to wait till the last day of the term. Nope. Gavin's not here yet. Sorry, I forgot that. Okay. Almost perfect attendance today. And by the way, I have your first test. I don't think you turned in the second test yet, have you? No. Okay. I'll need your second and third test today. And I've got your first test. I'll get back to you today. Turn those in right at the end of class. And if you haven't done your research paper, I need that in today too. Everybody. Did everybody here? I can't remember if I said that before, did I? Research papers are due in today. So if you haven't got them in, get them in to me today. If you don't get them in to me today, then you're losing points. Okay? So please get them in today. All right. And then almost finally, if the two vectors form an acute angle between them, then your dot product is always positive, because the magnitude of u and magnitude of v are always positive, and the cosine of an acute angle is always positive. Okay. Now, if the two vectors are collinear in the same direction, then your theta is equal to 0, the cosine is equal to 1, and it's just simply the product of the two magnitudes. That's going to give you the largest magnitude you can get. Okay? This will be the smallest you can get, meaning the most negative. That will be the most positive you can get. This will be positive, but not as positive as that. That one will be 0. This will be negative, but not as negative as that. So you get the general idea? So just the sign of the dot product is going to tell you something about those angles. All right. So that leads to this third feature there, leads to this. Definition of orthogonal vectors. The vectors u and v are orthogonal, meaning right angle to each other, perpendicular to each other, okay? Normal to each other, if and only if the dot product is 0. Meaning if the dot product is 0, they've got to be perpendicular. Okay. The two terms, orthogonal and perpendicular, mean essentially the same thing. They meet at right angles. Notice the 0 vector is orthogonal to every vector, because 0 vector times u, dotted with u, is always going to be 0. So see, this is the vector 0, that's the number 0. So up here, that 0 looks thinner, this one looks thicker, but not as thick as that. It's just the way they have it in notation. Typeset. Okay. Now, they're skipping example 4. So let's go back and do example 4. We'll do it right here. Okay. Determine whether these two vectors, U, and again, not necessarily a unit vector. As soon as you write it down, you see they're not unit vectors. 2, -3, because that magnitude is way bigger than 1. And V, vector V, which is 6, 4, even way, way bigger than 1. Determine whether those are orthogonal or not. What's the easiest way to determine if they're orthogonal? Plot them out on the graph and guess? No. Do the dot product. And what's the dot product of U and V? How do we do dot products? Anybody? Okay, you want to write them out? Is that what you're saying? Is that what you're saying? No, you don't have to. What were you saying? Okay. Okay. If you do 2 times 6, that's 12. And -3 times 4, that's -12. So that is 12 minus 12. And sure enough, that is 0. So therefore, you have just shown, proven, absolutely beyond a shadow of a doubt, those are orthogonal vectors. Okay? Good deal. All right, now we're going to find vector components. Okay? Seems like we've seen this before, haven't we? Okay? You've already seen applications in which two vectors are added to produce a resultant vector. Many applications in physics and engineering pose the reverse problem. Decomposing a given vector into the sum of two vector components. Frankly, I kind of did that anyway, but this is going to do it. Consider a boat on an inclined ramp. Seen something like this before, this figure. The force F due to gravity, that's this force, that always points toward the center of the earth. Straight down, perpendicular down from the horizon. Okay? Now, there are two components of that force. One component is pulling the boat and trailer down the ramp, and the other is what we call normal to the ramp, or perpendicular to the ramp. Okay? Now, why would we mess with that anyway? Well, because it's a force that you're going to be needing to predict and use. And the main reason is usually you need to know the force that pulling down, because that's the force you've got to exceed to pull it up the ramp. Okay? So that's why you need to break it into the normal, which I call the parallel component of the force and the perpendicular component of the force. That's how I like to think of them, and that's exactly what they're doing. But if you're thinking of the force to pull it up here, let's call that T or something like that, then this would be the opposite of T, and this would just be the other component of that. So the force due to gravity pulls the boat down the ramp and against the ramp. In other words, gravity is pulling that wheel against the ramp, that's the normal force, and down the ramp, that's what you're having to overcome by pulling it up the ramp. Okay. Blah, blah. Those two orthogonal forces, W1 and W2, are vector components of F. That is, you can break F into W1 and W2, and frankly, I like to call that W parallel and W perpendicular. But that's just my preference, okay? The negative of component W1, which is usually down the ramp, is one they did, represents the force needed to keep the boat from rolling down the ramp. That's exactly what it said. That's what you have to, the tension force you have to be pulling up with. Whereas W2 represents the force that the tires must withstand against the ramp, because that's the same component down like this is the component that the ramp is pushing up on the tires. So they have to be able to withstand that. Okay, the procedure for finding W1 and W2 is shown below. And don't make a huge mountain out of this. It's usually not that hard to do. Okay? Yeah. There's two possibilities, so I can't picture any boat ramps that do like this. So that's kind of not in the picture for the boat ramp, but you could have that in another application. Okay? The boat ramp would usually be in acute angle here. So the definition of the components, let U and V be non-zero vectors such that U is equal to W1 plus W2, where W1 and W2 are orthogonal with each other, and W1 is parallel to or a scalar multiple of the vector V, this other vector V. So W1 is in the same direction of W1. V and W1 are in the same direction. Okay. The vectors W1 and W2 are called vector components of U. Obviously, if they're perpendicular to each other, then they can be components. I call them parallel component and perpendicular component, or whatever your ramp is. Okay. The vector W1 is the projection of U onto V. Okay. So W1 is a projection of U onto V. So if this was your weight downward, project that up onto the bottom of the ramp, you might think that would be your W1. Okay? Projection of U onto V. Vector 2, W2 would then be the difference then between U and W1. Why is that? Because, let's just take this for an example. This is U, this is V. The projection of U onto V would be this vector, actually longer than V is. Okay? Then if you do, to get W2, you do W1, which is this one, okay? I'm sorry, U, which is this one, and subtract this from it, and that will give you, picture it this way. Put the initial side of V up here, the opposite direction minus V, put it back here, that gives you W2 in this direction. This vector subtraction. U minus V minus W1, that gives you W2. And that will turn out perpendicular every time. Okay. Now, to me, that's not the easiest way to do it, but it is a way to do it. From the definition of vector components, you can see that it's easy to find the component W2 once you have found the projection of U onto V. To find that projection, you can use the dot product. That's why they're mentioning it now. Okay? Now, as we said, U is a combination of W1 and W2, and these, we know ahead of time they are orthogonal. Okay, later we'll say prove they are. The W1 is some scalar multiple of V. Okay? So this is CV plus W2. The dot product of those would be CV plus W2, that's the U, dotted with V. Well, guess what? V dot V is, anyone remember?
Magnitude of V.
Second?
Magnitude squared of V.
The magnitude of V squared, and then the C times that. We may not use that yet, but that is another deal for it. So this would be CV dot V plus W2 dot V. So that's exactly what we get here. Okay? Using the properties we talked about last time. All right, where do we go with that? All right. From what we've already said, W2 is perpendicular to W1. Remember that was given. These are the perpendicular components. And since W1 is in the same direction as V, W2 and V are perpendicular to each other. So since they are, this dot product is 0. Okay? And that's all what you have left here is C times the magnitude squared, which is what we have here. C plus the magnitude squared plus 0, which is just C minus magnitude squared. So, C, and remember that's the scalar, that how much V was scaled up or down to get W1, okay? And that would then tell you how big that number is. It's simply the dot product divided by the magnitude squared. So the W1 is a projection of U onto V would then be CV, that is what W1 is, and that's U dot V over the magnitude of V squared, that's what the C is, times the vector V. So this gives you the scaling factor, and you multiply that by the vector V. So the projection of U onto V, U and V, the non-zero vectors, projection of U onto V is this. U dot V over magnitude of V squared times V. Okay. Now, don't know if this is helpful or not, but if you think that this V, take one of these magnitudes of V out and put it over here, this gives you the unit vector in the direction of V, and this is what you are multiplying that unit vector by U dot V over magnitude of V. Okay? But you don't need to do that. That's just a little aside. Okay. I think that leads us to example 5. Decomposing a vector into its components. Okay? Find the projection of U onto V, U being 3, negative 5, and V being 6, 2. Then write U as a sum of two orthogonal vectors, one of which is the projection of V onto U. Okay? So, let's first find the projection of U onto V. And this is the symbology of it. I want to make sure I'm saying that absolutely right. Projection of U onto V, right? Okay. So let's do it. What would that be? This thing right here, projection of U onto vector V. Well, we just did it. It's this thing, okay? Which is U, goodness, I can't write, dot V onto magnitude of V squared times the vector V. Okay. First thing we do, yeah, U dot V. And what is that? Okay. It's 18 minus 10, which is 8, over square root of 40. Now we can improve on that just a little bit. The 8 over root 40. What is root 40? Simplify it a little bit. Is there a perfect square lurking inside 40? Yeah, square root of 4. So that would be square root of 4 times the square root of what? 10. Okay. So this would be 8 over 2 root 10. And 2 will go into 8 4 times. So it would be 4 over root 10. Now, I have no objection to having radicals in the denominator. Okay. In the old days, it was important not to, but now it doesn't matter. But in case somebody is still in the old days, you could write that as what? 4 root 10 over 10, which then you could reduce to be 2 root 10 over 5. Okay? So you could write it either of those two ways. How did the book wind up writing it? Did they even write it? Oh, here we go. They left. Yo. Oh, wait. This is v squared, not v. Okay. So we just did a 40 down here, not root 40. Okay. So 8 over 40. Let's erase all this stuff. We'll come back to it in a bit. Okay. We didn't need that because it's magnitude squared, which the magnitude is root 40. Magnitude squared is just 40. So 8 over 40 is 1 over 5. Okay, so there's this part. That's your scalar part. That's the c. Okay? And then you multiply that by the vector v, which is 6, 2. So this will be 1/5 of 6, 2. And I guess that would be perfectly okay with me to leave it that way, but you could write this, think of this as 0.2, right? 0.2 times 6 is 1.2, and 0.2 times 2 is 0.4. There's another way to write it. I don't know if they do or not. Nope. They write it this way, which is perfectly fine too. 6/5, 2/5. Lots of ways you can write it, okay? Now, that is your projection of u onto v, is that vector right there, okay? It's in the direction of v, but scaled down to that vector there. Now, that is your W1. You saw that from before. That's the projection of this. This is what we call W1. Okay. That is I like to call it W parallel. That's the component of your vector u that's sort of doesn't make any sense in an abstract way to say parallel and perpendicular. But if it was on a ramp or something like that, that would be parallel to the ramp. Okay, so let's just call it W1. Okay, now we need to come up with a W2, and there's a couple ways to do that. The easy way, I guess, all of them are fairly easy. W2 would then be the u vector, which is 3, -5, minus the w vector, which would be 6/5, 2/5. This is why I really didn't want to go this route, but that's what sorry. God, my eyes are stinging. I think being right over this fan dries them out like crazy. Okay, so that would be this would be 15/5 minus 6/5 would be, is it that 9/5? Yeah, I believe that's right. And minus 25/5 minus 2/5 is minus 27/5. So I think that is your vector W2. And that's what they got as well. And then you can go back and add these two together to see if you indeed get that, and of course you do. Okay. So I don't know why they took you all the way around to do that. But anyway, there is a checkpoint right after that, so please do the checkpoint now. We've run out of time, haven't we? Yeah, I was thinking, getting close, but we got past close. Okay. If you want to follow up on this, you can do homework exercises 7 through 11. They're all at Calc Chat. 7's at Calc View. 13 through 21, they're all at Calc Chat. 21's at Calc View. 23 to 27 are all at Calc Chat. 29 through 37, they're all at Calc Chat. 31's at Calc View. 39 or 41, they're both at Calc Chat. 43 or 45, they're both at Calc Chat. 43's at Calc View. 47 or 49, they're both at Calc Chat. 47's at Calc View. 51 to 55, they're all at Calc Chat. 51's at Calc View. 57 or 59, they're both at Calc Chat. 59's at Calc View. 61 or 63, they're both at Calc Chat. And then there's a few more you can do if you want to play with those. All right. Now, before you go, for those who came in late, I need your test. And before you go, I want to give all of you the next two tests. One is the Chapter 6 test, and the second being the final exam. Okay? And for those who were not here at the very beginning, are either of you graduating this term? No? Okay. Your test, now you can return Chapter 6 test first if you want to, and then later turn in the final, or whichever order you want to, you can turn them in at the same time. Okay? But I have to have them, or I'd like to have them by the end of business on Thursday. Sooner if possible, but end of business. I'm here until 8 o'clock Thursday night. Okay? I will accept them up till 10:30 on Friday. Okay? I'll be here till 10:30 on Friday. Because at 10:30 I've got to leave to go to the Birmingham campus to watch that guy graduate. Okay? No, we all have to be at graduation. And I think they probably want us there by noon because graduation starts at 1. So I think I'll be leaving about 10:30. Wait, I said that right. 11:30. Okay, what have I been talking about? I'll leave here at 11:30. So get it to me by 11:30 on Friday morning. At 11:30, I'll leave to go to the Birmingham campus, and I have to be there by 12. And then after that, we'll be heading toward after graduation. I'll be leaving. So get me the things before, preferably by Thursday night, but no later than 11:30 Friday. Okay. Now, this says test 3. It's really test 4. I forgot to change the topic. So here's your Chapter 6 test. I'm being really lazy. Final exams slide it under my door. Okay? I'll tell you now, Wednesday from 4 till after 4 o'clock, I'll be on the Birmingham East Campus from 4:30 to 6:30.
Didn't you say you're gonna drop our lowest test grade?
Not your final exam. Okay. That's your final exam.
Okay.
I'm in Math 112. Ryan Edwards. Appreciate it. I would like my copy of the quiz and test.
Okay. All right. Any questions for y'all?
Hey,
Okay, let me see. I think I do, but I'll have to dig through and find it. Well,
there was something faster.
here we go. One piece or how many?
Just one more.
One more?
I was turning in my test and I was gonna say I don't have my research paper, but I mean, how many points are you gonna take it off if I turn it in late?
It depends on how late, but you know.
I try to have it at least before next class. At least by Friday, not Friday. I guess Monday, but more than likely Friday.
Or if you get it to me anytime today, there's no points off. Not today. Okay, well, get it to me when you can. It's not going to be a lot.
Okay.
But yeah, get it to me when you can. Did you turn in all your stuff?
I got it right here.
Okay, I need it. Okay.
You'll be here. You gonna be here all day?
Jackson.
I'm sorry?
So you're gonna be in here all day?
I'll be here until 8 o'clock tonight. But I've got class from 3:15 until 7:45.
Okay. You gonna be in your office like after this?
Yeah, I'm going to work here. I got to turn off this, so I'm not recording all this.